Hello friends, good afternoon and welcome to EduSite live lectures. Dear friends, today's topic for discussion is chemical thermodynamics, third law of thermodynamics. To discuss this topic with us, we have our subject expert Dr. Amit Kumar. Dr. Kumar is assistant professor in Department of Chemistry in the Dayal Singh College in University of Delhi. Without further ado, I would like to welcome sir to our studios and request him to start the lecture. Welcome sir.
Thank you very much, Amrit. First of all, I wish very good afternoon to all the viewers of this series, which is based on chemical thermodynamics. Dear viewers, we have been having a enormous number of lectures where we have covered in topics ranging from basics of chemical thermodynamics to the various laws also. For example, we had discussed the zeroth law of thermodynamics, the first law of thermodynamics, and the second law of thermodynamics. We also discussed the very purpose of introduction or having these laws and what are the various thermodynamic concepts and the concepts of various state functions which these laws, for example, internal energy, enthalpy and the entropy, these concepts were also discussed. In addition, how we can calculate the entropy change, internal energy the energy change and the enthalpy change for a chemical reaction, that has already been discussed. Now it is time for us to know how we can calculate the entropy change for a particular reaction. But in order to do that, first of all we need to talk about the molar entropies of substances. But in order to calculate the molar entropies of substances, it is important that we discuss the third law of thermodynamics. It is the third law of thermodynamics which actually makes up the discussion towards the calculation of molar entropies of substances. So let us see what is in store for us in terms of the third law of thermodynamics. Now if we want to understand the third law of thermodynamics, as I said, the third law of thermodynamics basically helps to calculate the molar entropy of a substance in a given physical state at specified temperature and at specified pressure. And if we talk about standard molar entropy of a substance, it straight away means that we are talking about molar entropy of a substance at specified temperature and at 1 bar pressure. In order to calculate these entropies, we require the third law of thermodynamics comes to help. In order to understand what actually is the third law of thermodynamics, let us consider a transformation, a physical transformation. Now let us consider a constant pressure transformation of a solid from the absolute zero of temperature, that is 0 Kelvin, to some temperature T, that is T Kelvin, below its melting point. So what we are talking about, the transformation is that a solid which gets heated from a temperature that is 0 Kelvin at pressure P to a temperature T Kelvin, again keeping the same pressure P. Now for this transformation, now the idea is that how we can calculate the entropy change. So if you notice it carefully, this equation which has been written, solid at 0 Kelvin at pressure P represents one state of the system, that is state 1, and when it gets heated to temperature T Kelvin, then it represents the state 2. So therefore the entropy change for this transformation can be calculated as entropy associated with the solid substance at temperature T minus the entropy of the same substance at 0 Kelvin under the condition of same pressure. So basically what we are talking about is the isobaric process in which the temperature is increased, and for a particular increase in temperature we want to quantify the entropy change. And if you remember back in our lecture, one of our previous lecture, we had given this formula that this entropy change can be evaluated by evaluating the integral from 0 to t Cp by t dt. This information, this formula was derived in our previous lecture, where we had discussed the entropy as a function of temperature and pressure. Now, we can rearrange this equation 2, which is nothing but the change in entropy, and basically let us see if we rearrange this equation 2 in a way that we take the entropy at absolute 0 of temperature from left hand side to the right hand side, the equation 2 transforms to equation 3. So, equation 3 now actually represents the entropy of a solid substance at temperature T at or below its melting point, that is equal to the entropy of the same solid substance at absolute 0 of temperature, that is 0 Kelvin, plus the term which correspond to the increase in entropy from 0 Kelvin to T Kelvin. Why we are saying increase in entropy? Because if you see the second term here in equation 3, here the Cp is a positive quantity. Cp represents the heat capacity of a substance. Since the heat capacity of a substance under constant pressure condition is a positive quantity, and T, which is again a temperature, is again a positive quantity. So, when the temperature increases, so it does mean the second term in this equation 3 will always be a positive quantity. It does mean that the entropy of a substance will always increase with increase in temperature. It therefore means that the entropy of a substance at absolute 0 of temperature will therefore be a minimum value, minimum possible value, or the smallest possible value. The entropy since increases with temperature, once again we can note that entropy since increases with temperature, and thus at 0 Kelvin the entropy of a substance should be a smallest possible value. Now, if we want to determine the entropy of a substance at some temperature, of a solid substance at some temperature of interest, let us say T, then we should have the values of two terms. One is we should be able to evaluate the integral, that represents the second term in equation 3. This integral can be evaluated if we are being able to measure the heat capacity of the solid substance under constant pressure condition. Moreover, we further require the entropy of the substance at absolute 0 of temperature. Now, the question is how to obtain the entropy of a solid substance at absolute 0 of temperature. The answer actually comes from the third law of thermodynamics, which is basically based on the Nernst heat theorem. According to the Nernst heat theorem, the entropy change for a reaction involving only pure crystalline substances at absolute 0 is 0. Being influenced from this Nernst heat theorem, Max Planck in 1913 suggested that the entropy of a perfectly pure and perfectly crystalline substance must be 0 at absolute 0 of temperature. And this suggestion then becomes the third law of thermodynamics, that is, the entropy of a pure perfectly crystalline substance is 0 at the absolute 0 of temperature. Therefore, entropy of a solid substance which is pure and perfectly crystalline at absolute 0 of temperature, therefore S0 is equal to 0. So, therefore, by utilizing the third law of thermodynamics, if we make use of third law of thermodynamics in equation 3, what we get is, if we put S0 is equal to 0, then we get the entropy of a substance at temperature T, which can be evaluated by evaluating the integral 0 to T Cp by T dt. So, this St, which is nothing but the entropy of a substance at some temperature of interest at or below its melting point, is also known as the third law entropy, because we are being able to calculate this entropy of the substance at some temperature of interest only with the help of zeroth law, only with the help of third law of thermodynamics, according to which S0 becomes 0. So, therefore, that is why this entropy of a solid substance at temperature T is called third law entropy. The third law entropy of a solid substance, therefore, is the value at 1 bar pressure. Now, this St naught as the superscript you can note in the symbol St naught. Here St naught represents the standard entropy of a substance at temperature T, that is the entropy of a solid substance at 1 bar pressure, which can again be evaluated using the same integral from 0 to T Cp by T dt, where P is nothing but 1 bar. Having said this, now a question comes. We can easily evaluate using these formulas, we can evaluate the entropy of a substance in its solid state of aggregation. But what about standard entropy of a liquid above the melting point of a substance at some temperature of interest, or at or up to its boiling point? In order to answer this question, or for that matter we can also ask this question, how we can determine the standard entropy of a gas above its boiling point. So, in order to answer such questions, we should keep in mind one thing, we should keep in mind that for any phase transformation, for such as vaporization process where a liquid transforms to vapor phase, or fusion process where a solid gets transformed to liquid phase, all these kind of phase transformations also involve the increase in entropy, and therefore, if we want to determine the molar entropy of a gaseous or a liquid substance, we must incorporate the entropy change corresponding to such phase transformations. As a result, now we can here develop equation 7 as the equation for calculation of entropy of a liquid at a temperature above the melting point of a substance. In equation 7, we can easily see that this has 3 terms. One term which is just nothing but it represents the increase in entropy of a solid from 0 Kelvin to its melting point, which can be evaluated by evaluating the integral from 0 to Tm, that is melting temperature, Cp standard of a solid at by T dt. Now, the second term actually is the contribution towards the increase in entropy when a solid undergoes transition from solid phase to liquid phase in the fusion process, and is evaluated as delta H standard fusion enthalpy change accompanying the fusion process divided by its fusion temperature or the melting temperature. Now, the third term represents the increase in entropy when a liquid gets heated from the melting point of the substance to the temperature of interest. This temperature of interest can be any temperature below or up to its boiling point. So, therefore, this third term we can evaluate as integral Tm melting temperature to some temperature of interest T Cp standard of liquid by T dt. So, using equation 7 we can therefore, in this manner we can determine the standard entropy of a liquid substance above the melting point of a substance. Now, coming over to determination of standard entropy of a gas at some temperature of interest above the boiling point of the substance. Now, you can see here the number of terms have increased from 3 to 5 in equation 8. St0, that this St naught actually represents the standard entropy of a gas at a temperature, specified temperature above the boiling point of the liquid. So, above the standard boiling point of the liquid. So, you can see first term just As is already been discussed, first term represent the increase in entropy when we heat a solid from 0 Kelvin to its melting temperature. Second term represent the entropy increase in entropy accompanying the fusion process in which solid gets transformed to liquid, and then the liquid gets heated from its melting point to its boiling point, and doing so it increases the entropy. The third term contributes towards that, and the fourth term then actually is the increase in entropy, represents the increase in entropy due to phase transformation, that is vaporization. So, its contribution is also incorporated, that is calculated by having enthalpy of vaporization divided by the boiling temperature, plus there is another term, that is now the last term, the fifth term here. This is an integral which is evaluated between temperature limit boiling point to the temperature of interest. Again, by having the heat capacity of the gases, standard heat capacity of gases species divided by the temperature into dt. So, evaluating this integral then determines the increase in entropy for this temperature change from boiling point to the temperature of interest. And in this manner you can see it means therefore, the calculation of standard entropy of a gaseous species at a temperature of interest actually involves at least these 5 terms, that is increase in temperature for a solid substance, the incorporation of term corresponding to increase in entropy due to fusion process, then heating of liquid, then due to transformation of liquid to vapor, and then the gaseous species which gets heated to the temperature of interest. All these processes lead to increase in entropy, and this sum up to give you the standard entropy of a gaseous species. Now, it is important to note that if a solid undergoes any transition from one crystalline form to the other, the entropy of the transition must also be included. Like you see, we have already considered that whenever a solid gets undergo transition from solid phase to liquid phase, there occurs an increase in entropy. It is also possible that there some of the substances may be existing in more than one crystalline form. So, when you heat them, what happens is one of the crystalline form of solid gets transformed to the other crystalline form. This is also a phase transformation process, and therefore, during this phase transformation process also the entropy of the substance increases, and therefore, we should also calculate the entropy change corresponding to such phase transformations, and we should also incorporate such entropy changes in order to evaluate or in order to determine the standard entropy of a substance, whether in a solid phase or in a liquid phase or in a gaseous phase at the temperature of interest. So, now what is important to note is that the third law of thermodynamics actually helps us to determine the standard entropies of a substance in a given physical state. Now, what it requires? It requires evaluation of various integral terms and incorporation of phase transition terms. So, in evaluation of these terms actually requires the accurately measured heat capacities of the substances in the range of temperature in which they are required. Moreover, we also require enthalpies of transition and the transition temperatures. So, these are mandatory conditions for the determination of standard entropies of a substance in a given physical state at the temperature of interest at 1 bar pressure. Having said this, this is all it means. Third law of thermodynamics is therefore is a very useful law. Why? Because once we determine the standard entropy of a substance, that we can make use of in calculation of standard molar entropies of a given reaction, that we will see shortly. But now the fact of matter is that for only a few solids we are being able to determine the heat capacities at such low temperature, that is few hundredths of a degree above 0 Kelvin. For all other substances, for most, in fact for most of the substances, we are not being able to accurately measure experimentally the heat capacities at such low temperatures, and we can only therefore can go up to some lowest temperature where we can accurately determine the experimental values of standard heat capacities at constant pressure. And this lowest temperature may range from a solid to solid, and the temperature range may be somewhere lies somewhere in between 10 Kelvin to 15 Kelvin. So, it means the first term integral which require the evaluation of entropy change within limit 0 Kelvin to melting temperature we cannot accurately determine. So, now the question comes how to actually account for this difficulty. Now, here the Debye T cubed law comes into help at this point of time. Let us see how the Debye T cubed law helps us in evaluating third law entropy of a substance. Actually, what happens is that according to the Debye T cubed law, heat capacity at a constant volume is equal to A, which is constant characteristic of each substance and varies from substance to substance, times the cube of temperature. So, this is just a very simple law, Debye T cubed law, using which if suppose at 12 Kelvin for a substance I am being able to determine the experimental value of heat capacity at constant pressure. Now, since at such low temperatures the heat capacity at constant pressure and constant volume values are indistinguishable. So, what can I do is I can determine Cp and can substitute for Cv here in this Debye T cubed law, and I can divide the temperature at which I have carried out this heat capacity measurement, say 12 Kelvin. So, using this Debye T cubed law, therefore, I can determine the value of A, the constant characteristic of the substance at the lowest temperature at which I am being able to determine the heat capacity value experimentally. That is in this manner, evaluation of constant A using Debye law. I have just rearranged the Debye law and I have determined A using Cp value at T dash temperature. T dash is that temperature at which I am being able to determine the heat capacity under constant pressure condition. So, I have substituted the Cp in place of Cv in Debye T cubed law at temperature T dash and multiplied with T dash cube. So, in this manner the Debye T cubed law helps me to determine the value of A. Moreover, what the Debye T cubed law does is that allows me to split the integral, that is the integral 0 Kelvin to T Kelvin Cp standard S by T dt in two splits that integral in two terms. One term represent the integral 0, one term represent the integral from the temperature 0 Kelvin to some temperature T dash, which is the temperature at which I am being able to experimentally determine the heat capacity value. So, therefore, up to this T dash I do not have the experimentally determinable heat capacity value. Now, the second term which represent the integral from T dash to Tm, that is the melting temperature, Cp standard by S by T. Since Cp standard value I am being able to determine within temperature range T dash to Tm, suppose for example 12 Kelvin to that melting temperature of the solid. So, it means I can easily determine the second term of equation 11. Now, the question is the first term actually here also in place of AT cube, Cp should have been there, but using d by t cubed law, I am just writing in place of Cp AT cube. And since I have evaluated the value of A at lowest temperature T dash, so I will just put that value of A here in this first term of the first integral term, and I will make use of T cube by T dt, and I will then evaluate this integral as T standard 0 to T dash AT cube by T dt. Now, I will further suppose that this A will not vary with temperature within this temperature range 0 to T dash, that is the lowest temperature at which I can determine experimentally the value of heat capacity, standard heat capacity. It may be 10 Kelvin, 11 Kelvin, 12 Kelvin, 13, 14 or 15 Kelvin. It usually range between 10 to 15 Kelvin. So, it will be that temperature. So, in this manner, now therefore, it is very clear that the zeroth law of thermodynamics in itself is not able to help us actually to determine the standard entropy of the substance, but it also require the help of d by t cubed law. Then only we can determine the standard entropy of a substance. But now let us see the two terms which are being represented here. How we can question is, we can easily evaluate mathematically, but can we also look at some graphical solutions towards the evaluation of the integral, such as second integral which I have written over here in this equation 11? The answer is yes. Let us see how we can do that. I just write this second term in equation 11 at the left hand side of equation 12. Now, see how I can split it up. Since 1 by t dt is just nothing but d ln t, derivative of natural logarithm of t is nothing but 1 by t dt. So, in place of 1 by t dt over here in the left hand term, I have just written d ln t. Now, since ln t, which is natural logarithm of temperature, I can just write as 2.303 log to the base 10 t. So, that is what I have done. I have taken 2.303 common over here and written the integral from t dash to tm Cp standard s d log 10 t. So, I can evaluate this second integral by plotting either Cp standard with d ln t, Cp standard by t with t, or I can do what is I can plot Cp standard of a solid versus d versus log to the base 10 t. The area under the curve so obtained is therefore the value of the integral. For example, if I plot Cp by t versus t, so I will evaluate the area, whatever the graph I will get, the area within the curve actually will represent the evaluated value of this integral, and this integral is also equivalent to the right hand side integral, which actually is just nothing but is evaluated by plotting the standard heat capacity of substance versus log T in Kelvins. Since logarithm, if you plot, it should be a dimensionless quantity. So, therefore, now whatever the area which is shaded within the curve, it is the evaluated value of this right hand side integral. It should be multiplied with 2.303. So, we can determine the second term. So, therefore, third law of thermodynamics along with d by t cubed law helps us to determine the standard entropy of a substance, a solid substance, a liquid substance or a gaseous substance. But the third law of thermodynamics is different from zeroth law, first law and the second law of thermodynamics. The basic difference is that the third law of thermodynamics lacks the generality. What we mean by saying that it lacks the generality? If we say that it lacks the generality, it do mean that it is not applicable over all substances. Not every substance do follow this law. This law is being followed by only a special class of substances. and such substances are nothing but pure, perfectly crystalline substances. Although this law lacks generality and cannot be applied over all substances, yet is very useful law since it helps us to calculate the molar entropy of at least for pure perfectly crystalline substances. So, therefore, this law is very important along with the Debye-T cubed law. Now, there are a number of substances which are pure perfectly crystalline substances as well, but their entropy at absolute 0 of temperature is not 0. So, what it does mean? It is not that all perfectly pure crystalline substances are being found to follow the third law of thermodynamics. It means there are exceptions which also exist to the third law of thermodynamics. It means such substances do not follow the third law of thermodynamics, which straight away means that those substances which do not follow third law of thermodynamics, they would still have entropy values at absolute 0 of temperature. If they have entropy values associated with them even at absolute 0 of temperature, it does mean that we now need to designate this in the form of a new concept called residual entropy. So, those substances which are exceptions to the third law of thermodynamics and therefore do not follow the third law of thermodynamics, they possess residual entropy. So, residual entropy we can make as a concept is the value of entropy associated with a pure perfectly crystalline substance at absolute 0 of temperature. I can also cite certain examples of certain chemical species, certain substances which possess residual entropy. The examples include carbon monoxide. Carbon monoxide having a residual entropy of 4.6 joule per Kelvin per mole. Nitric oxide is another example with having 2.8 joule per Kelvin per mole as residual entropy. Crystalline hydrogen also is another example with 6.23 joule per Kelvin per mole as its residual entropy. In addition, the ice also possesses residual entropy at 0 Kelvin, and the experimentally determined value echoes with that of the theoretical value as well. Now, having said this, the question arises actually why it is that there certain substances possess residual entropy and why others do not, or in other words, what is the reason behind the substances possessing residual entropy. Residual entropy. Now, the fact of matter is that we will take up this discussion of residual entropy further once actually we describe the statistical interpretation of entropy. The entropy change, before that we take up another important aspect which we had described as the goal of our discussion today, that is entropy change in a chemical reaction. Now, entropy change in a chemical reaction can easily be evaluated in the same manner as we do evaluate the enthalpy change for a chemical reaction, but with one little difference. We shall take up this difference. Let us first of all define standard molar entropy change in a chemical reaction. That is given by delta S standard, that is the standard molar entropy of a reaction, which is nothing but the difference between the standard entropy of products and that of the reactants. And the standard molar entropy of a reaction is therefore can be calculated as sum of stoichiometric coefficients nu p times the standard molar entropy of products less the sum of stoichiometric coefficient times the standard molar entropy of reactants. If we want to understand what we mean by how we can calculate the standard molar entropy of a reaction, we can take up a reaction. For example, for this reaction between Fe2O3 solid plus 3H2O, that is 1 mole of Fe2O3 combines with 3 mole of hydrogen in the gaseous state, then it forms 2 moles of iron, and in addition it also gives 3 moles of water in liquid state. Now, the temperature of the reaction is 298 Kelvin and the pressure is 1 bar. Now, if we want to evaluate the standard molar entropy of this reaction at 298 Kelvin, so what we require? We require the values of standard molar entropy of iron in solid phase, water in liquid phase, Fe2O3 in solid phase, hydrogen in gaseous phase at 298 Kelvin and at 1 bar pressure. And it should be made very clear that these standard molar entropies can easily be evaluated, using the Debye T cube law along with the third law of thermodynamics as specified and as stated earlier. So, this data is available in Handbook of Physical Chemistry, and therefore, for any given chemical reaction we can easily make use of such data and we can calculate the standard molar entropy of a reaction. For example, stoichiometric coefficient of the product 1, which is iron in solid phase, is 2. So, we multiply 2 with standard molar entropy of iron in solid phase at 298 Kelvin at 1 bar pressure, and add to this is the, since stoichiometric coefficient of water in liquid phase is 3 as another product. So, we add to this term is the second term, which is 3 into standard molar entropy of water in liquid phase. From this sum we do subtract the sum of standard molar entropy of Fe2O3 in solid phase, because its stoichiometric coefficient is 1, plus 3 times the standard molar entropy of hydrogen in gaseous phase, since 3 is the stoichiometric coefficient in this balanced chemical equation for this hydrogen gas as one of the reactants. Now, it is important to note that what difference actually lies in the evaluation of standard molar entropy and standard molar enthalpy. The standard entropy of elements in their most stable state of aggregation is not considered as 0. That is exactly opposite to what we used to consider in the enthalpy values, because the standard enthalpy values for most stable state of aggregation of elements were considered as 0. But here it is not so, that is the basic difference. And now we can make use of the same equation and the same formula, and we can tabulate the experimental data. For example, standard molar entropy of iron in solid phase is 3.2 R. R is gas constant, which has the value 8.314 joule per Kelvin per mole. Whereas standard molar entropy of water in liquid phase at 298 Kelvin is 8.41 R, and the standard molar entropy of Fe2O3 in solid phase is 10.51 R, and standard molar entropy of hydrogen gas is 15.70 R. So, just by tabulating the data corresponding to standard molar entropy of these various product and reactant chemical species in this given formula, for calculation of standard molar entropy of a reaction at given temperature, we can determine its value, and which turns out to be, for this particular equation, which turns out to be, by having this numerical value as minus 214.7 joule per Kelvin per mole. Now, for this reaction, as we have already calculated, the standard molar entropy for this reaction at 298 Kelvin is minus 214.7 joule per Kelvin per mole. Now, we can consider another reaction where Cu2O, cuprous oxide, combines with coke, that is carbon in solid phase, again at 298 Kelvin and at 1 bar pressure, and do form 2 atoms of copper 2 moles of copper and in solid phase, and in addition also gives carbon monoxide 1 mole in the gaseous phase, again at temperature 298 Kelvin and at pressure 1 bar. So, now in the same manner, we just by using the formula that standard molar entropy of a reaction can be calculated as sum of stoichiometric coefficient times the standard molar entropy of products less the sum of stoichiometric coefficient times the standard molar entropy of reactants. We can calculate the standard molar entropy of this particular reaction as well, which is represented by symbol delta as standard M 298. And I have not shown here the mathematics involved, but it turns out to be that its value turns out to be plus 158 joule per Kelvin per mole. Now, you can make a distinction. We have here two reactions. For one reaction, we have when the reaction occurs, that is reaction 1, when the reaction occurs, the entropy of the system decreases, whereas for reaction 2, the entropy of the system increases. The temperature is maintained same, both the reactions are carried under standard conditions, that is under 1 bar pressure. Now, the question arises, why it is so that in one reaction there is an enormous increase in entropy and the other reaction there occurs an enormous decrease in entropy? The answer is no difficult to find. The fact of matter is that if we consider the fact that in equation 1, for reaction 1, here the condensed phase Fe2O3 combines with a gaseous phase, non-condensed phase hydrogen gas, and forms only condensed species, iron in solid phase and water in liquid phase. Moreover, if we compare this reaction 1 with reaction 2, what happens in reaction 2? Both the species are in their most condensed states, that is both the species cuprous oxide as well as coke, the carbon, both are in solid phase, and they lead to the formation of copper 2 mole in solid phase. In addition, a gaseous species gets generated. So, it means in one reaction when the entropy decreases, when the entropy of the system decreases by virtue of having reaction 1, because reaction 1 is actually consuming a non-condensed phase, and we all know that for a phase transformation, there occurs an increase in entropy when a phase transition occurs from a condensed phase to a non-condensed phase. So, it means for the reaction in which a condensed phase is produced at the expenditure of a non-condensed phase, or in other words, when the gaseous species are consumed and lead to the formation of condensed species, then the entropy is bound to decrease. Moreover, in addition, we can see when the condensed phases reacts to form a non-condensed or gaseous species, then of course the entropy usually is found to increase enormously for such reactions, and therefore, by virtue of comparison between these two reactions at same temperature and under standard conditions, we can easily visualize why there are certain reactions for which entropy will usually increases and there are others whereas for them the entropy usually decreases by virtue of reaction. Now, the question arises, if we know the standard entropy of a reaction at one specified temperature, then can we know the standard entropy of the same reaction at another temperature? Now, if we look at the formula for calculation of standard entropy of a reaction, then it requires the standard entropy of products and reactants. So, therefore, it means we need to have standard entropy of products and reactants at different temperatures if we want to calculate standard entropy of the reaction at different temperature. But we can solve this difficulty of requiring standard entropy of products and reactants at different temperature by making a little derivation. We can derive this formula for standard entropy of a reaction itself with respect to temperature, keeping the pressure of the system constant, that is 1 bar. Now, if we do differentiate, it means we can write del of delta S standard by del T, which is equal to nu P del of delta S standard, this is not delta S, this is S standard products by delta T at constant P minus nu R del of not delta S standard but S standard reactants by delta T. So, it should be noted here in equation 18, this delta sign and this delta sign in both these first and second terms should be eliminated, then the equation becomes a correct equation. So, now having said this, now this del S by del T at constant P is nothing but, by the definition of heat capacity, is the heat capacity of standard heat capacity of a substance if we utilize standard entropy. So, therefore, this is just nothing but is equal to nu P, that is stoichiometric coefficient of product, into standard heat capacity of products by temperature minus nu R, that is stoichiometric coefficient of reactant species, Cp standard reactants, the heat capacities of reactants by T. If we take the T common and we can write it as delta S standard, delta S standard is just nothing but the standard entropy of reaction by del T by delta T, which is equal to delta Cp standard by T, where delta Cp standard is just nothing but the difference of heat capacities of products, each multiplied by difference of two terms. One is sum of stoichiometric times the heat capacities of products, and the other term is stoichiometric coefficient times the standard heat capacity of reactants, and that is how we get delta Cp standard by T for a particular reaction. Now, we can rearrange this equation 19 and we can write it in the differential form. We can take this delta T towards the right hand side and we can rearrange, and what we can get is, then in that situation when we take this dt to the right hand side, we get d delta S standard at constant P at constant pressure equal to delta Cp standard by T dt P. Now, this differential equation we can easily integrate within the temperature range, the reference temperature range from T0 to any other temperature T. What we mean by this temperature range? We mean that if suppose we know the standard entropy of the reaction at temperature T0 and our objective is to determine the standard entropy at some other temperature T, then we can make use of this differential equation and we can integrate this differential equation between temperature range T0 to T. Let us see how we do that. When we integrate this differential equation, we get integral T0 to T d delta S standard which is equal to, now integrating this right hand side term, integral T0 to T delta Cp standard by T dt. Now, what is this left hand side? This is differential of this delta S standard, that is entropy of reaction. So, it means delta S standard at temperature T minus delta S standard at temperature T0, which is equal to integral T0 to T delta Cp standard by T dt. Now, we can further rearrange equation 22 in a way that we can take delta S standard at temperature T0, this second term, to the right hand side and it becomes a positive value, and delta S T standard, that is the entropy change of reaction at temperature T, standard entropy change of reaction at temperature T becomes equal to standard entropy change of the same reaction at temperature T0 plus the integral term which involve the integral from temperature T0 to T delta Cp standard by T dt, where delta Cp standard is just nothing but the difference of standard heat capacities of products and reactants, each multiplied with their stoichiometric coefficients in a balanced chemical equation. So, now this delta S standard T naught, which is just nothing but the entropy change of a particular reaction at a temperature T naught. T naught is that temperature at which its value we do know, and we can add to this the evaluated value of the integral term, and the addition of the two terms then determine the entropy change of the reaction at another temperature T. So, this is how, by virtue of this relationship being derived, we need not have the standard molar entropy values of various chemical species at different temperatures, but if we have the standard molar entropy values of the various participating chemical species which do participate in a chemical reaction, we can make use of those values at a particular temperature. We can determine the entropy change for a reaction at that temperature, and we can using this relationship determine the entropy change for the same reaction at some other specified temperature. This is how we do determine the entropy change for a particular reaction under standard conditions. So, in this lecture, what we are being able to till this point of time to understand is that what is actually the third law of thermodynamics, how it does help us to calculate the standard molar entropy of substances, that is also it requires the help of from the Debye T cubed law, and using these standard molar entropy values of various pure perfectly crystalline substances, we can determine entropy change for a number of chemical reactions. Now, one thing we did left in this discussion is that there are certain exceptions to the third law of thermodynamics also, and we did say that those species do have residual entropy, and the residual entropy we said that can only be understood once we do discuss the statistical interpretation of entropy or the interpretation of entropy with the probability. So, it is now time to discuss the statistical interpretation of entropy, what actually the entropy has to do with the probability. That is what therefore is our next topic of discussion. Let us have a brief introduction about this, and we will cover it up in our next lecture in full. So, let us have a brief idea of what actually we are going to deal with. Statistical interpretation of entropy actually is that according to this the entropy of a system in a definite state can be related to what is called the probability of that state of the system. Now, it is very difficult to understand how we can have a relationship of entropy and the probability of the system, or what is actually the probability of the system. So, there are two things to be understood. One is that how to make up the relationship between the entropy of a system and the probability of the state of the system, and in fact actually what is actually the probability of state of the system. So, therefore, these are the two important questions which would be for the discussion. For statistical interpretation of entropy, it is essential to have a structural model. So, we all know that if anyhow we have to discuss the probability, then we need to have some structural model of the system, then only we can talk about the probability, suppose the occurrence of such arrangements or chances of the system being there. So, all this discussion, the discussion of probability, need the structural model of the system. You see, now it is important to make a distinction between the fact that entropy, if we take up from the standpoint of the probability distribution, then it means that statistical interpretation of entropy in contrast to its thermodynamic thermodynamic definition, which does not require any structural model of the system. Here if we want to have statistical interpretation of entropy, then we do require the structural model of the system. And now question arises, what kind of structural model we are talking about? So, basically by virtue of structural model, for simplicity we would consider that the system is composed of a large number of particles, small particles or molecules. That is what would be our structural model. And we will do consider some natural observations, as I also discussed during the thermodynamic definition of entropy also, that why there are certain changes which we never observe. For example, leaves from trees, they do shed in the autumn, and no one has seen dry leaves attaching themselves to the branches and rising themselves and coming to buds and then once again going back. So, this observation is nobody has seen. Similarly, now let us consider one more example. The example is that suppose a small box is taken up and is placed in a room, and this box is filled with a gaseous species at 1 atmosphere pressure. Now, this box is placed in a room. This room is perfectly sealed as well as evacuated. Now, the fact of matter is, now suppose that after some point of time the walls of the box are released. What will happen? We all know the gas does not have a size and a shape. It acquires the shape of the vessel in which it is placed. So, now when the walls of the small box is taken away, then each molecule of the constituent, each molecule of the gas is free to move and will therefore uniformly fill the space. This is an observation we can easily make. But has anybody ever noticed or ever seen that the gaseous species which is filled in a room, they do collect themselves in a small volume element in one corner? Nobody has seen that. Again, another observation we can say that if we have a balloon which is filled with a gaseous gas, and now if we pierce the balloon then shrinks. The gas molecules do escape. But nobody has seen the gaseous species themselves coming into the balloon and once again making the balloon as it is in its shape. So, the fact of matter is there are certain observations which are never observed. From the statistical point of view, we would try to answer these questions and we would like to shed light on thermodynamic aspects from the standpoint of statistical interpretation of entropy. That will be taken up in the next lecture. Thank you so very much for this lecture, for hearing this lecture. Thank you.
I would like to thank sir for this enriching lecture, and thank you friends for watching. Stay tuned and keep watching. Thank you.